Hi everyone, welcome to the course of structural biology again. We are continuing with structural biology techniques and I am continuing also with crystallography. Today is very interesting. We are going to talk about 3 dimension, their unit cells, about symmetry, about the lattice and all. And I always feel that this part is very difficult to understand. So, I have taken a kind of different way to explain those things, starting from one dimension to further. To start with, I will start with a small drama about 3D. An unspeakable horror seized me. There was a darkness, then a dizzy, sickening sensation of sight that was not like seeing. I saw a line that was not a line. I saw a space that was not a space. I shrieked aloud with agony. Either this is madness or is this the hell? Ha ha ha! It is neither, calmly replied the voice of the sphere. It is knowledge. It is 3 dimensions. Open your eye once again and try to look steadily. So, again, this is taken from a novel called Flatland, and they also told distress not yourself if you cannot at first understand the deeper mysteries of spaceland. By degrees, they will dawn upon you. As I told, this is the thing which came when squares first encounter with 3 dimension in the E.A. Abbott's Flatland, the novel. So, you understand the spaceland as they told. If you have to start with point land, a point, then you have to go with from 0 dimension of the point land to the 1 dimension, which is a line land. From 1 dimension line land to the 2 dimension flat land, and from the 2 dimensional flat land to 3 dimensional space land. That is what they told in the novel, A Romance of Many Dimensions. Do not worry, I am not talking about romance at all, but today we will talk about many dimension which reflect the study of protein crystallography. We will start with 1D lattice. 1D lattice is a journey from a point land to the line land. So, let us imagine, because in reality there is not a 1 dimensional crystal. So, we will talk about space lattice first. Space lattice are an array of points in space such that every point has identical surroundings. So, that is what the formation of crystals. If you have a point, you get the other point in a equidistance or identical position. Whichever point in the lattice you choose, space should look identical to you. So, you are sitting here or you are sitting here, you should see everything, the space, the 3 dimension identical. And if that happen, this will automatically implies to 2 properties of lattices. One is in Euclidean space lattices, there are in infinite array. If you see in this direction, in this direction, in this direction, in this direction, it is going in an infinite goal. Lattices have translational periodicity. Here the word periodicity is important. If you look at, this is a perfect lattice and you see the periodicity here, translational periodicity. This is a polycrystal, you do not see it as organized like this ideal crystal, but you see local periodicity, and this is amorphous where you do not see any translational periodicity. So, infinite array infinite array and translational periodicity are the two things which connect the space lattice. As I told, let us start from 1D lattices, and as it does not exist really, let us construct a 1D lattice toting with 2 points. So, this is one point and this is another point, and this develop the 1D lattice. So, this is a 1D lattice at the simplest form. A point on the right has a point in its left. So, if you think this point and this point, for this point it have a point at the left, and but this does not have a point at the left. But and as I told, the requirement is of identical surrounding. So, it also have a point here, but in a similar logic these have a point here. So, these also have a point here. So, one of the left should have one more to the left, these have one more to the left. At the same argument, there should be more to the left and more to the right. So, this should have one more in left and right. This would lead to an infinite number of points, because a new point come, it would lack a point in this or this direction, and if you keep continuing, this would lead to infinity as we have discussed. So, we have to go to infinity for a proper 1D lattice. The infinity on the sides would often be left out from schematics. Sometime when you want to represent, you cannot represent infinity. So, this is again the 1D crystal with a distance between the 2 points A. So, in 1D there lattice, there is only one kind of lattice, and this lattice can be described by a single lattice parameter, which is A, the distance. In 1D, the action of a mirror operator is same as that of a twofold or a inversion parameter. So, here you do not have difference. If you have a point, you have a mirror, you get one point, but that relation is same with inversion and rotational axis. So, here the mirror symmetry, twofold axis and inversion play same result. In 1D, the mirror and the twofold axis reduce to a point, which means the mirror in 1D is no longer a plane, but a point. Similarly, a twofold axis is not a line, but a point. In the 1D lattice, the mirrors are at lattice point M0 and midway between them is M half. Other symmetries, threefold, skew axis, etc. does not exist in the 1D lattice. The unit cell for this lattice is a line segment of length A, like this. Coming to the next level, 2D lattice, which is a journey from the line land to the flat land. So, a line to a square box. This is a representation of a 2D lattice with x and y axis. The two basis vectors generate the lattice, they are A and B, and the angle is alpha. So, the basis vectors, there are two basis vectors A and B. There are three lattice parameter which describe the lattice, which are A, B and alpha, the angle. Here for this lattice, alpha equal to 90 degree. So, in 2D lattice, there are 4 unit cell shapes in 2D and they could be used for 5 lattices. They have square where A equal to B and angle equal to 90 degree, rectangle which is A, B and alpha equal to 90 degree, and 120 degree rhombus where A equal to B and alpha equal to 120 degree, and parallelogram where they have AB and alpha of any. Though they are called lattice parameters, it is better described as unit cell parameter because they are more defining the unit cell. There are 3 lattice parameters in 2D, 2 distances and 1 angle, which we showed earlier with A, B and alpha. So, if you look at the lattices, there are 5 type of lattice: square, rectangle, center rectangle, 120 degree rhombus and parallelogram. We are coming to symmetry later, but shape of the unit cell, square, both for rectangle and central rectangle, they are rectangle, 120 degree rhombus, they are rhombus, and parallelogram, they are parallelogram. So, there are 4 lattice with 5 unit cells. Now, we are shifting to the 3D lattices where actually we want to deal with, because the protein crystals or any crystals we are talking about, they are mostly defined by 3D lattices. So, it is a journey from flat land to the space land which is our dream journey. So, 3D lattices could be generated with 3 basis vectors. The unit cell of, so who are the vectors? A, B and C, which are showing 3 axes x, y, z. The unit cell of a general 3D lattice is described by 6 numbers. In special cases, all these numbers need not be independent. They are called 6 lattice parameters. There are 3 angles ABC, which are also the 3 basis vectors, 3 distances and 3 angles alpha, beta, gamma. This is a general 3D lattice. If you see here, A, B and C are not equal, and whereas alpha, beta, gamma is also not equal, the lattice parameters. In special cases, some of these numbers may be equal to each other, like A could be equal to B, B could be equal to C, or A could be equal to B equal to C, or equal to a special number, that is A equal to B equal to C equal to 90 degree or something like that. And to give a good example of a specified 3D lattice, we are coming next. So, in those cases, we may not require 6 independent number to describe a lattice. So, when it is a general 3D lattice, we have A, B, C, 3 distances which are also the basis vector, and alpha, beta, gamma as angles. So, we have 6, but if some special things come like A equal to B equal to C, then we would have A equal to B equal to C represented by S, and 3 angles. If alpha equal to beta equal to gamma, then we have another angle. So, we have the distance S and the angle theta, only 2 parameter in that way. Such an example is 3D cubic lattice where A equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degree. Actually, this is a part of the cubic lattice because the lattices are infinite. As I told, these could go to infinity. Each vertex of the cube is a lattice point. So, now we are in the 3D lattice, we are coming to crystal, which is where our topic is there. A crystal or crystalline solid is a solid material whose constituent atoms, molecules or ions are arranged in an orderly repeating pattern extending in all three spatial dimensions. We have talked about this. We have our molecule is going to unit cell and unit cell is going to crystal. That is the journey talks about. Crystallography, we have already talked about this, but to refresh our memory, is a study of those crystals to understand it in molecular level. We want to understand not the crystal here, rather the molecule which is inside the crystal, because by making crystallography or by making a crystal, we just enhance the signal which is coming from the molecule, because the atomic level signal was not possible to find from a single molecule. We have discussed that. Early studies of crystal were carried out by mineralogists who studied the symmetries and shapes of naturally occurring mineral specimens. That is what the starting of or foundation of crystallography, where protein crystallography is indebted. This lead to the correct idea that crystals are regular three-dimensional arrays. These are called Bravais lattices of atoms and molecules. A single unit cell is repeated indefinitely along three principal directions that are not necessarily perpendicular. One of the fundamental concept of crystallography is that crystals are made up of millions of identical motifs or unit cells. For our case, we understand that because we do crystallography because we need our proteins to be in millions, so that the signal would be very enhanced and we could get good signal. This is a two-dimensional unit cell. This is similar to the motif in a wallpaper pattern. Note that the environment in the each corner of the cell is the same, which we have shown. If we ignore the color difference, there is also fourfold symmetry at each corner and also in the center and at the midpoint of the each edge. As we will see, symmetry is also important in the study of crystal, where we are coming later. Unit cell, the smallest repeating unit of the crystal lattice is the unit cell, the building block of a crystal. The unit cell, which are all identical, are defined in such a way that they fill space without overlapping. The 3D arrangement of atoms, molecules or ions inside a crystal is called crystal lattice. It is made up of numerous unit cells. One of the three constituent particles takes up every lattice points. So, coming to Bravais lattice, it's actually the system was invented by Auguste Bravais. Here is the picture of him. In 1848, he demonstrated that in a three-dimensional system, there are 14 possible lattices. A Bravais lattice is an infinite array of discrete points with identical environment. 7 crystal system plus 4 lattice centering type equal to 14 Bravais lattices. We are going to discuss again later about that in details. Lattices are characterized by translational symmetry. This is very important, because think about when you are going to read symmetry, you already know about symmetries like mirror, like inversion, like rotation. So, if you only consider translation, then where would be the other ones? So, that is one of the biggest confusion started that time, which is cleared now and I will talk about. A lattice is a set of points constructed by translating a single point in discrete steps by a set of basis vectors. As we talked about, when we are talking about 1D, it is the A, when you are talking about 2D, it is AB, and when you are talking about 3D, it is ABC. They are the base vectors. The 3 dimension, there are 14 unique Bravais lattices distinct from one another in that they have different space groups in 3 dimension. All crystalline material recognized till now fit in one of these arrangement. That is the beauty. All crystalline materials recognized till now are fit into this model. In geometry as well as in crystallography, a Bravais lattice is an infinite set of points generated by a set of discrete translation operation. They are mostly depending on translation. A Bravais lattice, that is what Bravais used to think. A Bravais lattice looks exactly the same no matter from which point in the lattice one views it. It is the same I told, when you are in one point, you go to another point, be in your any side. If you are on the lattice, all those points should behave identically. You should see the space land identical way. Bravais concluded that there are only 14 possible space lattice. This belongs to 7 crystal system. There are 14 Bravais lattices which are the space group symmetries of lattice. But a critical thing to discuss, and it is very interesting. Crystals and crystal system are defined based on symmetry, not based on the geometry of the unit cell which we were talking about. So, Bravais majorly talked about geometry, whereas they are defined and properly fit when you consider symmetry. As I talked earlier, because that is the surprising thing, what the fact? So, if lattices are based on geometry, there would only be translation, then how come other symmetries, especially rotational, come into the picture while choosing the crystal system as well as unit cell for a lattice? Also, why do we say that end centered cubic lattice does not exist? So, if you will go further, you will see this is a cubic lattice, and each of the cubic lattice have primitive face centered and body centered, but not end centered cubic. So, why we do not have? The issue comes because we want to put 14 Bravais lattices into 7 boxes, the 7 crystal systems we are going to discuss. The Bravais lattices have 7 distinct symmetries and further assign unit cell to them. The crystal systems are defined based on symmetries, rotational, mirror, inversion, etc., forming the point groups and not on the geometry of the unit cell. So, first of all, we knew that the classification of crystals are not based on geometry. So, it is not based on geometry, it is based on symmetry, and now we know that this is the point group which are important. The choice of unit cell is based on symmetry and size. So, symmetry is extremely important. Coming to symmetry, Symmetry is a state in which parts on opposite sides of a plane, line or point display arrangements that are related to one another. This relatedness happens via any of the symmetry operation such as translation, rotation, reflection or inversion. Application of symmetry operators leaves the entire crystal unchanged. So, initially we talked about the point coming to something and then get the unique positions. Now, we are talking about that movement going from one point to the second point of the lattice should be done based on the symmetry operations. So, what are the basics of symmetry? The order is predicted by symmetry resulting from observing how atoms are arranged and oriented in a crystal lattice. Study the 2D and 3D order of crystal from small molecules and proteins. This is performed by defining symmetry operators. There are total 13 symmetry operators, not independent, they are independent and combined actions which result in no change to the order of atoms in the crystal structure. Combining different operators give point groups which are geometrically unique units. Every crystal falls into some point group which are segregated into 6 major crystal systems. Elements of symmetry identified in the unit cell will be present in the crystal. So, element without translation, translation is definitely one. Elements without translation, mirror which is reflection, center of symmetry which is inversion, rotation and glide. These are all referred to as symmetry operation. So, we talked about the lattices, starting our journey from 1D lattice to 2D lattice and 3D lattice. I hope you get the idea how the lattices are developed and you understand also the upliftment from your journey from point land to line land to flat land and ultimately coming to space land where you deal with the crystals. We have also looked at Bravais lattice, which we will discuss even more at the later part. We started our concept of symmetry, which is a very important concept in protein crystallography, because more symmetry you get, you reduce your work. What I mean? Suppose you have this unit cell, and in the unit cell you have 16 atoms, means 16 protein molecule. So, you have the unit cell with 16 protein molecule. Now, you are solving the structure. If you get one symmetry, it will be reduced to 8, 2 symmetry 4, 3 symmetry 2, 4 symmetry 1. So, instead of development or building up of the model of 16 molecules, now you have to just work on one molecule. You understand the level of our advantage when we find symmetry. So, with that I finish this class, today's class, and I will meet you next day. Thank you very much for listening to me. I hope I will get you in the next class also. Thank you.